here we go. I'm a rookie at this too, so if I look funny playing Video Master, then that's why. Okay, matter and atoms. Every living thing, every non-living thing is made of matter. Matter is anything that takes up space and has mass. Matter is made of very small particles called atoms. Atom is the smallest unit that cannot be broken down by chemical means. An atom has a positive charged core, middle, center spot, surrounded by a negatively charged region. Now here is the old-fashioned model of an atom. We have a new, improved, better model, and it looks like this. It's called an electron cloud. Electron cloud. The nucleus in the middle right here, this little spot in the middle is called the nucleus, has two things. It has protons and neutrons. Okay? Now the protons are positively charged, and the neutrons have no charge at all. Then flying around on the outside is electrons, and they are negatively charged. They fly around so fast that you can't see them. It just creates a blur. Just a blur. Okay? And that's what this is. This is the cloud, which represents the blur from the electrons moving so fast. Now I want you to notice, I don't know if you can see, let me turn the lights off so you can see a little better. Notice there's a kind of a dark blue ring right there and another dark blue ring right there. Those are levels, or shells. And that's where the electrons mostly hang out, is in these levels or shells. Now the first level contains 2 electrons. The second level contains 8, or it wants to contain 8. And then once it gets 8, it makes a new level. And then that makes 8, it makes a new level. Then it just builds from there. But 8 is very important. It wants to have 8 electrons there. Oh, speaking of which, if we were in school 2,000 years ago, way back in the old day, we'd learn about 4 different elements. Only 4. Does anybody know what the 4 old elements are? Anybody watch Airbender? Nobody knows? You guys need to watch more TV. Fire, earth, water, and air. Those were the 4 elements of the old. But now we have modern elements. In the modern day, we have 92. And elements are basically different kinds of atoms. Different kinds of atoms. They're determined what kind of element they are by the number of protons. For example, there is the chart. Let me turn the light back on because we've got to talk about the chart. This chart up here looks better. Today we have to learn about 92 elements, from 1 to 92. From 1 to 92. Now, you have 2 choices. I need you by tomorrow, by the next class tomorrow, I need you to memorize all 92 elements.
Wait, but it's Saturday tomorrow.
Tomorrow, the next day of class tomorrow. Tomorrow, the next day of class, which is Tuesday.
Oh.
Okay? All 92. Or, if you don't want to learn all 92, then you just learn how to use the chart. Now, if you learn how to use the chart, then you say, look up here. The first element is hydrogen. It's way up there. The letter is H. And the atomic number is right there. 1. That means it has 1 proton. Okay? And then the mass number is also 1. It's 1.00 something something. We don't care about all the points and the little numbers after. We just round it to the nearest number. That is the mass number. That basically means the total number of protons and the total number of neutrons. So if you have 1 proton and the mass number is 1, how many neutrons does it have? Can anybody do their math? 1 minus 1 equals how many?
0.
0! Who said that? Oh, you're so smart. You didn't even have to use a calculator or anything. Okay. That's basically how you play the chart. Look at number 2. Number 2 is helium. Has an He for a symbol. 2 is the atomic number, that means 2 protons. And the mass number this time is 4. 4. So how many neutrons does helium have? It's easy. 4 minus 2 equals what? 2. Yeah, you didn't use a calculator again. You're so smart. All right, and that's basically how you run the chart. Now, some examples. There's an example. Oxygen is an example. Gold is an example. Oh, speaking of gold, check this out. Come back over to the chart. The gold is right here, 79. But its symbol is AU. Who was on drugs when they came up with AU? How can they come up with AU for gold?
I'm sorry, it's just AU reminds me of the initials for alternate universe and such.
Yeah, that's not why. Good guess.
Isn't it Greek?
Latin. Yeah, gold is very old. In fact, when they discovered gold, nobody spoke English. Guess what they spoke? Latin. The scientists, that is, spoke Latin. And so they came up with AU for the gold name for inland, which is, I don't know what it is. I better figure that out. I used to know. I just know it starts with AU. Okay, again, these are just some models of atoms. Atoms are so small we can't see them, so we like to make models so we can understand them. Oh, speaking of hydrogen, hydrogen is the smallest of all the elements. This is kind of interesting. In fact, there's more hydrogen than all the other elements in the world. In fact, there's more hydrogen in the universe than all the other elements. Lots of hydrogen. And hydrogen is what causes the sun to burn. The sun creates energy for us because it does something called nuclear fusion, where you take a little atom, another little atom, you combine them, and you make a new element called helium. Okay, plus it creates a whole bunch of energy. That's what we use. And we use that same kind of energy to make what's known as the hydrogen bomb, a thermonuclear explosion caused by fusion of atoms. Check this out. The largest of all the elements is uranium. This is uranium ore right here. Come over here. 92. Uranium is 92. And it's the largest naturally occurring element in the world. And we have uranium in Utah. In fact, we have uranium mines in Utah. So we're kind of cool that way. But, speaking of uranium, scientists take uranium and process it and change it into this element called plutonium. Plutonium. That's a plutonium sphere. Plutonium is over here also. 94, it's different because it's a man-made element. It doesn't occur naturally. And it's 94. Then they use plutonium to make this. This is a nuclear atom bomb. Atom bomb. And that's nuclear fission. They create the explosion. And this is an actual picture of an actual atom bomb going off. Let's turn the lights off again so you can see it better. This is the same kind of bomb we used to blow up Japan. Now, a lot of people are upset about us. We blew up Japan. I'm sorry about that. But remember, we first blew up Nevada first. So that kind of makes it okay. Then, after we blew up Japan, guess what we're blowing up right here? This is Bikini. This is right next to an island called Bikini. They went out in the middle of nowhere and blew it up. they like to play. It's like they had firecrackers and they were playing with them, except they were super powerful explosions. You don't have to know that, but it's just kind of fun, interesting to talk about. Oh, check this out. I guess we're going to talk explosions a little bit more. This is the hydrogen bomb. The hydrogen bomb uses an atom bomb as a fuse. It's like the fuse just to get it going. And then they release this green gas called tritium. At the same time, and that tritium is hydrogen gas, a special hydrogen gas that causes this super explosion, 1,000 times bigger than the bomb that dropped on Japan. Kind of scary. Okay, but we need to get into stuff. So we want to talk about chemical bonds. The electron cloud of an atom has many levels. The electrons in the outermost level are called valence electrons, and they are the key to causing chemical bonds. In the outside energy level, we want 8. There it is, 8. We want 8 in that outside energy level. Okay? And they do things like sharing electrons or stealing electrons or giving electrons away in order to create that stable outside energy level with 8 electrons. And so electrons are the key to making compounds and molecules, which means atoms and elements are combined. Okay, molecules, compounds, I'm going to kind of go over this. Let's listen to this movie.
The outer shell of many atoms, hydrogen being an exception, holds 8 electrons. Atoms that have an outer shell containing 8 electrons are considered chemically stable. We often say they fulfill what is called the octet rule. When atoms combine to form compounds, they can give up, accept, or share electrons in order to assemble an octet of electrons in their outer shell.
Okay, octet refers to 8. Octet means 8, so they're trying to get those 8 electrons on that outside energy level.
A covalent bond is formed when atoms share electrons in order to satisfy the octet rule. For example, a carbon atom holds 4 electrons in its outer shell, but it would be much more stable with 8. To gain the additional 4 electrons, carbon can share with other atoms, and thereby have a completed outer shell. If one carbon and 4 hydrogen atoms come together and share their electrons, carbon achieves an octet of electrons. Note that each hydrogen in this compound achieves 2 electrons in its outer shell.
Okay, so there is a picture of something called CH4, methane. That is an important compound, hydrocarbon, but it's made by sharing electrons, so that's called covalent bonding. Now, let's look over here, because the one I want to talk about today is written over here. This is another very important compound. This is the compound we're learning about today. This is 1 oxygen and 2 hydrogen. Oxygen has 8 electrons, but 6 electrons in the outside energy level, so it's missing 2. So it shares with 2 hydrogens and end up making this molecule H2O, H2 hydrogens, and 1 oxygen. Does anybody know what this is?
Water.
Water. Very good. Very good. And water looks like, what does water look like? Anybody know who that looks like?
Mickey Mouse.
Mickey Mouse. Yeah. Don't forget that. I think it looks just like Mickey Mouse. Oh, dang it. Back up.
To gain the additional 4 electrons, carbon...
Oh, Mr. Haskell, you're messing up on TV and video.
4 hydrogen atoms come together and share their electrons. Carbon achieves an octet of electrons. Note that each hydrogen in this compound achieves 2 electrons in its outer shell. This is the stable configuration of the first electron shell. An forms when two atoms are held together by the attraction between opposite charges. The reaction between sodium and chlorine atoms is an example of how an ionic bond is formed. Since sodium has only one electron in its third shell, it has a tendency to give up that electron. Once it does, the remaining outer shell contains 8 electrons. This loss of an electron gives sodium a slightly positive charge. Chlorine, on the other hand, tends to gain an electron.
You watching this? This is cool.
When chlorine gains an electron, it becomes slightly negative. The charged sodium and chlorine atoms are called ions. Ions of opposite charge attract each other and form ionic bonds. In this case, the attraction of sodium and chlorine form a molecule called sodium chloride, or table salt.
So, ions are atoms who have a negative or positive charge because they've lost or gained an electron. Now, I like this chart here. Let's review this. So, we have sodium. Okay, normally sodium has one too many electrons. One too many. So it has one electron at outside energy level. So it's very unstable. So it says, hey, that outside electron, you should leave. Go away. We don't want you. So it kicks it out. Now it's got 8 electrons in that outside energy level, becomes very stable, very happy, and it goes on its merry way. Except it becomes positive because it lost one of its negatives. Okay? Now chlorine is bigger, and it has 7 electrons in its outside energy level. So it just needs one more to be happy. So it steals electrons from somebody, like sodium possibly, and it ends up with that extra negative electron, so it ends up with a negative charge. Now, this is where it gets very interesting because opposites attract. And the chlorine looks up here and sees sodium and goes, oh, sodium, look at you. Sodium, you have a positive. Look at that plus sign. Holy smokes, that's hot. You look so good. I can't believe how good you look. And sodium looks down at chlorine and goes, holy smokes, chlorine, you have a negative. I love negatives. They really get me going. And so sodium says, hey, chlorine, why don't you come on over here? Let's get closer. Maybe we get closer. We can make a connection. Because they attract each other, so they get together, they make an attraction, and they create a chemical bond called sodium chloride, which we know as salt. Salt. All right, that is ionic bond. Now, but we want to talk about water, so let's talk about water. Water is one of the most important molecules in life. It may have one oxygen, 2 hydrogen. And, yes, it looks like Mickey Mouse. Water has many unique properties that make it important to life. Okay? Most of the unique properties all have to do with something known as molecule. It becomes a polar molecule and makes hydrogen bonds. Now, let's come over here and look at this. So, what does it mean that water is polar? Water is polar, what does that mean? It's right here. Okay, here is my water molecule. Notice all these electrons down on this side. So this side of Mickey's face is negative. Mickey's face has got a negative charge. But his ears are where the protons are. No electrons, so they are positive. They have a positive charge. So this is what causes a polar molecule, which means it has positive side and a negative side both. Now, this is what gets fun. This gets fun. Okay, check this out. Oh, we're going to skip that. We'll come back to that maybe. Okay, so here's a bunch of waters, and this is where it gets cool. Because now we have Mickey here. He has a chin right here. And he looks over at this ear and he goes, ooh, look at your ear. It's positive. Hey, ear, why don't you come on over here? And the ear looks at Mickey's chin and goes, hey, you got a negative charge. Oh, I love negative. Holy smokes, you think I can come over there and touch your chin? And that's what they do, they attract each other. So the water gets together and they go, hey, I like your chin. And the ears go, and the chin goes, I like your ear. So they get together and they grab their chin, they grab their ear, and they start making connections. They make a bond. Guess what that bond is called? It's called a hydrogen bond. So water likes to touch water. Water likes to connect with water. So when you put water on a piece of wax paper, it forms a little fat drop. Because water likes to touch water, stick to water, because they're all holding on to each other's chin. That's a property of water called cohesion. Water likes to cohese together. They like to glue themselves together because of being polar, making hydrogen bonds, grabbing their chins and their ears. Hydrogen bonds. So that's what a hydrogen bond is. When water, stuff like water, likes to touch their ears and touch their chins. Cohesion is when water wants to touch water, but what happened when you put a water drop on the paper towel? What happened? Somebody brave, tell me what happened.
It's kind of spread.
Yeah, it's spread out. Because water likes to touch the paper towel. They go, ooh, paper towel, I want to touch you. So it touched some paper towel, then it touched some more paper towel, and it just spread out, and you end up with a big wet spot on your paper towel. That is called adhesion. So water likes to touch other things also. In fact, it likes to touch other things that also have some slight polar properties. So paper is also made out of stuff that is polar. So if you put your water drop on here, the paper will absorb the water, or the water will want to touch the paper. But when we put the water drop on the wax paper, did the wax paper absorb the water? So water doesn't like wax. And wax doesn't like water. So water didn't want to touch it, so it just tried to touch itself. That's why you got a big old fat, tall water drop. So some things, we're going to find out later why wax doesn't like water and water doesn't like wax. Oh, all right. Paperclip, check it out. Mr. Brooks, still floating. A paperclip is still floating. Did you know it's actually impossible for a metal paperclip to float on water? It's impossible. It's too dense. It cannot float. So how the heck am I getting that to sit on top of the water? It's actually not floating. It's just sitting on top of the water. It's just sitting there. How is that working? Because of cohesion, the water is grabbing their chins and their ears and holding on. And they create something known as surface tension. A little bit of tension on top of the water. Because all the water is holding onto their chins, onto their ears, not letting anything pass. So if you very carefully set your paper clip on top of that, and the paper clip is dry, if the paper clip's wet, it'll never work. It has to be a totally dry paper clip. Put it on there. Don't break the surface tension. It can stand on top of the water. Just like water skiers. Just like water skiers can also walk on water because they don't break that surface tension. All right. Okay, water, because it's polar, it has hydrogen bonds, it can dissolve stuff. Remember salt? Well, let's look at this. I like this little graphic. Because water dissolves salt. Remember that sodium chloride that thought they liked each other so much they wanted to get together and make a connection? Well, they weren't very loyal to each other. Because as soon as water shows up, check it out. Here's chlorine. Chlorine goes, hey, Mickey, you have ears that are positive. I like positive. And the ears go, hey, chlorine, you're a big negative molecule. Come on over here. Let me touch you. And they separate. Sodium right here says, hey, look at Mickey's chin. I like your chin. Come on over here, chin. I'll come over to you. And they leave each other and separate and divide. That's called dissolving. So when you put your salt in the water and stirred it up, the water disappeared. Or not the water, the salt disappeared, became invisible. But was it still in there? How do you know it was still in there? How do you know the salt was still in the salt water? In the water?
It tastes good.
What did it taste like?
Salt.
Yeah, you can still taste it. Even though you couldn't see it, you can still taste it. Alright, so anytime you dissolve something, you create something known as a solution. And we're going to come back to solutions in just a minute. One other thing. What happened when you put ice in water? Hello, Earth Calling class. Avery? Did you put some ice in the water? You didn't? Did anybody do the last experiment?
Yes.
What happened?
Floats.
It floats. Ice floats. Frozen water floats on top of liquid water, which is really unusual. Most of the time when stuff gets cold, it becomes more dense and it would sink. But ice doesn't do that. This is what happens. So here's liquid water, and here is frozen water. When the water freezes, the molecules all arrange so each ear is touching a chin, and each chin is touching the ear. And that causes it to expand. So when you freeze water, it expands. Now, I learned this lesson a long time ago because I like to drink Pepsi. And I love really cold Pepsi, so cold it's just a little bit slushy. So I got some Pepsi cans, and I go, I would really like it to be slushy. So guess where I put it? Put it in the freezer, and I go, I'll leave it in there for about 10 minutes, then I'll go check on it. It'll be all slushy, it'll be way good. Guess what I forgot? I forgot I put it in there, and guess what happened? That Pepsi can, which is clear full of water, froze and expanded, and it blew the can up, and I had a mess everywhere, and my mom yelled at me, and I had to clean out the whole freezer. Because water expands when it freezes. Now, is that a big deal? Is that a big deal to life? Is that a big deal to biology? Yeah, it's a big deal. Think about this. This winter, when it gets cold, and we have a Salem Pond out here, and it freezes, the ice stays on top. But if the ice sunk to the bottom, guess who gets frozen? All the stuff on the bottom. It freezes, and then more ice goes to the bottom. It freezes, more ice goes to the bottom. Pretty soon we have a solid frozen pond. Guess what happens to all the fish in the pond? They die. Guess what happens to all the plants in the pond? They die. All right, listen up. Finish this